welcome back to this next half. In the last half I have been talking about modules, module homomorphisms, generating sets, finitely generated modules, etc., etc. Now I want to introduce what are called algebras over a ring. So to motivate this, first I will take a simple case, that of a field. So my base ring now is a field, K is a field. So this is, if you like, I will call it a base field. It is not necessary, but just for the sake of motivation. Alright. So now what I am trying to define is algebra over K. Also this is sometimes abbreviated as K algebra. So same as this. So what is a K algebra? K algebra is a ring. So there are two things. B, this B is a ring. So I will write B equal to B plus and dot ring. We will assume it is commutative. If this is not commutative, we will have to modify the definition little bit. It is worth it, but I will do it after this. So B, first of all, it's a ring, and also at the same time it is a K vector space with respect to the same addition, and B plus is a K vector space with the same this is same addition, because it is abelian group, this is also abelian group. And this, so this means what? This means that this abelian group has a K scalar multiplication by K. That means we have such a map, K cross B to B, and the scalar multiplication map is denoted by A times X, this goes to AX. Such a scalar multiplication is there, and this scalar multiplication and this, of course when you say vector space, this scalar multiplication and this addition is compatible, that is the vector space axioms, and this scalar multiplication and this multiplication in the ring, that is also compatible. That means what? That means, so compatibility. Compatibility conditions. So vector space conditions I will not write. Vector space axioms, K vector space axioms on B, that is this addition and this field axiom, and also now this scalar multiplication of K scalar multiplication on B and multiplication in the ring B. So now for example, if I have a scalar A multiplied by element in B, this is scalar multiplication, another one, now there are elements in B, so now I multiply them in the ring. On the other hand, I could multiply X and Y in the ring and A and B in the field and multiply a scalar. So these two should be same for all A and B scalars and for all elements X and Y in B. Then you call it an algebra. Instead of writing so much, this is equivalent to saying, see, all this data is equivalent to saying there exists a ring homomorphism phi from K to B. Once I have a ring homomorphism, then I can define a scalar multiplication which satisfy these properties, and once I have a scalar this data, then I can define phi. For example, let me just write down a definition of phi using this. So, that is any A. Now, I want an element in the B. So, what can I do? So, take A times 1b. See, I have given a scalar multiplication, that means I have given this map a comma x going to Ax. So, in particular I can take x equal to 1b and then take this a equal to this map phi A is by definition A times 1 times b, and then check that this is a ring homomorphism. Conversely, if I have a ring homomorphism, I can define a scalar multiplication. And how do I define that? So, given phi, how do I define this map k cross b to b? So, take any a, take any x, and where can I send it? I have given this phi. So, obviously I can apply phi to a. So, phi a, I get an element in a and then multiply it by x. This makes sense because we have given this, and this is a multiplication in the ring, this is scalar multiplication. Now, so this is in one-to-one correspondence. So, it is easier to think ring homomorphism means, and so different scalar multiplications here, different k vector space structure on the same B plus will give different ring homomorphisms, and different ring homomorphisms will give different algebra structure. So, this one so in short, let me now be in short, an A algebra and K algebra is a pair. Which pair? It has two B comma phi, where phi is a ring homomorphism from K to B. And this phi is called the structure homomorphism of the K algebra B. If I have different homomorphism, then I will have a different algebra structure. So, when you say algebra, that means this phi is fixed. So, that is a pair. Now, just in this definition and in all this discussion, we never really use the fact that K is a field. So, you could have taken arbitrary commutative ring. So, similarly, if A is an arbitrary commutative ring, then an A algebra is a pair B comma phi, where B is a ring and phi from A to B is a ring homomorphism called the structure homomorphism. Okay, now just one comment here and we will see some examples. As I said, here I wrote B just a ring. So, normally we assume commutative in this course whenever I write, but in this particular case one can also allow non-commutative rings, but then you have to put a condition on this ring homomorphism. So, with this ring homomorphism should have a property that the image of this phi of A should be contained in the center of B. This is the center of B. This is the center of B. What is the center? That is by definition all those elements B in B which commute with every other element of B. So, B times C equal to C times B for every C in B, that is called the center of B. If B is commutative, then this condition is automatic. So, we do not have to write this condition explicitly, this is automatic. This condition is immediate, clear if B is commutative. This is what usually people who work in especially representation theory of groups, they will need to put this condition because the rings may not be commutative. I will also give one example where the ring may not be commutative, but it is very useful to study. Okay, now we should see some examples of algebras. The most important example, some examples. Examples. So, I will write for, so if A is any ring commutative always, then the polynomial ring over A in several variables A k x1 to xn, A x1 to xn. This is the polynomial ring, the polynomial ring in x1 to xn over k over A, that means the coefficients are in. So, in symbols this is summation. The polynomials in these variables look like this: nu equal to nu n to nu n in n power n, a nu, x nu. And what is this notation x nu? This is a calculus notation. This is x1 nu 1, xn nu n. This is a monomial corresponding to this n tuple nu in the variables x1 to xn, and these are the coefficients, and these a nus are in the ring A, and this is a finite sum. Any polynomial look like this. So, a nus are element in A. One says that for almost all tuples this is 0, only a nus are 0. So, that the sum is really a finite sum, and it makes sense, and that is a polynomial in a typical polynomial in this polynomial ring. And now, to say that this is an A algebra, what do I have to give? I have to give a algebra homomorphism from, I have to give a ring homomorphism from A to this. So, the phi, this one, there is a natural map phi there. This is a natural map, so I will call it iota. This is any A going to A itself. Think of A as a polynomial. So, this is a natural inclusion map. So, this is the, therefore, this A x1 to xn comma this iota is an A algebra. More generally, if you have any ideal, if A is an ideal in this polynomial ring x1 to xn, any ideal, then A to A x1 to xn followed by that pi, this is A x1 to xn modulo that ideal A, this is a quotient ring, and then we have this natural map pi which maps any polynomial f to, we have written f plus A, but we will write this as f bar. So, this composition iota composition pi is a ring homomorphism. This is, both these maps are natural maps, they are canonical maps. So, therefore, this quotient ring also you can think as an algebra over A with this as a structure homomorphism. So, A x1 to xn modulo the ideal A, comma iota compose pi, this is a ring homomorphism. So, this is an A algebra, and these are the algebras we want to study more. These are the algebras which will come in our algebraic geometry very often for different A's, and therefore, we have to study this algebra. Now, the next will be when do you say an algebra is finitely generated algebra, for example. So, but before that I have to give little more examples. So, the second example, any ring B is a Z algebra in a natural way, or maybe I will formulate little bit better. So, we are taking the base ring to be Z and B is any ring, any commutative ring, commutative. When I will tell you when the ring is not commutative, otherwise all our rings are commutative. Then there is a unique Z algebra structure on B. So, that means, so that is, in other words, there exists a unique ring homomorphism from Z to B. This I will denote by chi B. And what is that? So, if I tell you, we know under ring homomorphism 1 has to go to 1B. That is the part of a definition of a ring homomorphism. Once you know 1 goes to 1B, then arbitrary n, where will it go? It has to go to 1B plus 1B n times if n is non-negative. If n is non-negative, this is n times. Otherwise, it is minus 1B plus minus 1B n times minus n times if n is negative. So, this is the only ring homomorphism, and that will give you a unique structure of Z algebra on B. Okay. Now, the third one is non-commutative, and that is the only example I would like to study for non-commutative case. So, my base ring is a field now, A is K is a field and V is a K vector space. Then to each vector space I have these endomorphisms of N kV. What is that? This is simply, see, this V is a K module. So this is home kV, VV. So what does this mean? These are all linear operators on V. F, V to V, V to V. F is K linear. They are also called operators. This is obviously a ring because I can compose. Composition is a multiplication. So, and addition is a standard. How do you add two linear maps? So, then N kV is a ring with composition as multiplication. So, this is N K V plus and composition, and this ring is not commutative. If dimension of V as a K vector space is at least 2. In that case, you can find two linear operators F and G from V to V, K linear operators, such that F compose G and G compose F, they are not equal. So, dimension at least 2 you need because you need to play little bit. So, that I will leave it for you to check. So, this is also called ring of endomorphisms. Of V. Well, if V is finite dimensional, if dimension of V equal to n in n is a finite dimension of dimension n, then this ring NKV is isomorphic to MNK. What is MNK? MNK, this is their matrices A. So, I will not use that Gothic letter. So, Aij 1 less equal to I comma j less equal to n, and these Aij's are in the field, and you know how to add matrices, etc. So, this is an isomorphism. Any linear map, that is, if you choose a basis V1 to Vn, this linear map is uniquely determined by the matrix of F with respect to this basis V1 to Vn. So, this is the isomorphism. Given a matrix, we can define a linear operator, and given a linear operator we can this, but this is with a fixed basis. Okay. So, and okay, so that is this is therefore commutative ring, and there is a natural map. Okay, so let me go to the next page. There is a natural map from K to endomorphisms of A. What is this natural map? This is also inclusion map. So, namely any A in K, where do you map it? To that scalar. So, that means I have to define a linear map, that is usually denoted by theta A from V to V. This is V going to AV. This is called homothecy by A. So, they correspond to what they call it a scalar matrix. The matrix of any basis of this homothecy is theta A with any basis V1 to Vn. If it is finite dimensional, then this is nothing but A on the diagonal and zeros everywhere. That is clear, because V1 will go to A, V1, V2 will go to A, V2 and so on. So, this is unique, and this is obviously a ring homomorphism. So, this is a ring homomorphism. Moreover, the image of this iota of K, this goes inside the center of this endomorphism ring of V. Note that the center is nothing but the scalar matrices. A matrix commute with every other matrix when it is a scalar matrix. So, this is precisely, in this notation it is theta A, where A varies in K. So, our second condition, when we said that it is an algebra, that is satisfied in this case. So, with this endomorphism ring of V is a K algebra in a natural way. This map iota or with iota as structure homomorphism. And by now you would have realized that this endomorphism algebra is the object of study in linear algebra. So, you see linear algebra. So, this linear word corresponds to the every element is a linear map, and this algebra correspond to the fact that this endomorphism ring is actually K algebra. That is why the subject is usually called linear algebra. If people are studying only matrices, then it is usually called matrix algebra, and the matrix set of matrices is also an algebra. So, these are the only non-commutative examples of K algebras are studied very extensively in a extensive way, but other non-commutative algebras are rarely studied. Okay, so now let us go on. Now I want to recall or define the concept which is analogous to the finite generation. So, now we have seen when is the module finitely generated. So, now remember the module has operation only addition, which is underlying abelian group, and a scalar multiplication from a ring where it is a module over which ring. But in case of algebra, now we have two structures. We have a scalar multiplication of the base ring, and also we have a multiplication in the ring itself, that algebra itself, that is a ring multiplication. So, with this, so A, let us say A is a base ring. Whenever we have a difficulty or the questions are not easily answerable, one should specialize this ring to a field and then ask what is the answer, and then you can go on in a general setup. A is a base ring and B is an A algebra. Strictly speaking, one should write B comma phi, but I will drop this in the notation because it is understood there is only one ring homomorphism where we will make, there are many ring homomorphisms, but each one of them will make a different algebra structure. So, when you say B is an algebra, that means your algebra structure is fixed, that means this phi is fixed. So, therefore, we will not keep writing it in every time. Okay. Now when do you say a B algebra? What do you mean by sub algebra first? Let us say sub algebra. Like we have defined in case of a ring, we have defined ideals. In case of modules, we have defined sub modules, quotient modules. Quotient modules I have not defined, but I will come to it. We will define it. So similarly, we will define now first sub algebras. So sub algebras. So an A sub algebra of B, what is that? Is a subset B prime of B such that, so whatever operations you have, when you restrict those operations to this subset B prime, first of all they should restrict, and with those operations it should become an A algebra. So what does that mean? That means first of all B prime plus, this is a subgroup of B plus. So in this it is the same plus. Not only that, B the dot also, this should be a subring. Subring. Remember, we will have identity in the subring. Many books they do not insist that the subring should have the identity element also, but identity with respect to the multiplication. So it is a subring, and also the scalar multiplication of A should restrict to scalar multiplication on B prime. So B prime, so B so scalar multiplication, so A cross B to B we have the scalar multiplication. This is A scalar multiplication, that the same one should restrict to B prime. So you see here this is a subset here, and that map the image this way should go inside B prime. So this will induce A scalar multiplication on B prime. Then we call this B prime is a sub algebra of B. Now for example, how do you find examples of sub algebras? Again you do the same stuff, same funda. So examples, if you take for example, if you take any element x in B, now if I just take this is an A submodule, but this may not be closed under multiplication. So what you have to do is you have to take powers of x and generate a submodule. So that means you have to take the sum x power n, n in n. Now it is closed under multiplication. I made it closed under multiplication. So this is A sub algebra of B, and we will say it is generated by x. So what are the elements here? You see, elements are finite sums, finite A linear combinations from 1, x, x square and powers of x. But isn't, and the elements are not unique. Remember, two finite sums may be equal without the corresponding coefficient being equal, because this x is not a variable, it is not a, there are polynomials in x, but the expressions are not unique. So this also actually strictly speaking it should be denoted by A square bracket x. So this is a sub algebra generated by x. So this, just this notation is not enough. So this is, and there is no speciality about 1x. So, that is where I want to assume the algebras are commutative. So, if I have finitely many elements x1 to xn, then I should write this notation A x1 xn. Now, what is this? These are a linear combinations among the monomials in x1 to xn. So, this is same thing as summation. Now, this summation is running over the tuples nu equal to nu n to nu n and coefficients in A. So, I will write A and here I will write x1 nu 1 xn nu n. So, this is clearly an algebra and this is called A sub algebra generated by x1 to xn. And again it is, we can always take not only finite family but arbitrary family, and you can consider A sub algebra generated by that arbitrary family. Okay, so this is, when do you call algebra to be finitely generated? When there are finitely many elements such that the sub algebra generated by x1 to xn equal to B. So, B is called finitely generated A algebra if there exist finitely many elements x1 to xn in B such that B equal to A x1 to xn. Some examples. The most prominent example is this. If I take the polynomial algebra, A capital X1 xn in variables x1 to xn over A is a finitely generated A algebra. Moreover, this x1 to xn is an A algebra generating set for the A algebra A x1 to xn. Yes, also this finitely generated algebra also it's also called finite type over A. Finite type over A, that is also used in the definition. So, I think with this I will stop, and when we come next time I will give more examples, and then eventually we will get back to our study of algebraic sets and the geometry. So, I will keep shunting between algebra and geometry now and then to recall the concepts from algebra and use them in a geometric language. So, that will always be our strategy in throughout this course. So, we will continue in the next lecture. Thank you.